This instructional video will show all the steps from beginning to end for making slip-cast microporous membrane bulbs. Here is an example of a finished bulb having a major OD of 1.9 centimeters and length of 5 centimeters with a 10 millimeter stem. The bulb has an exterior surface area of about 40 square centimeters square, making it ideal for various tests carried out in a 1-inch OD pressure barrel. The bulb is hollow with a uniform wall thickness of about 1.5 millimeter, as seen here in cross-section. Slip casting is the only way to fabricate such a shape from ceramic. When bisque fired, these bulbs have a microporous structure with about 35% open porosity and provide a variety of useful applications. They may be coated with a diffusion barrier of metal or glass, used as a porous support for electrolysis palladium deposition for hydrogen separation, infused with catalyst to make membrane reactors, or used in the bare state for gas separation. When fired, the stem may be inserted into a 10 millimeter graphite ferrule in a standard Swage-lock 10 millimeter metaless steel compression fitting. A 10 millimeter to 1/4 inch union is used to interface with standard 1/4 inch stainless steel tubing for making a gas-tight connection from the bulb interior to the external gas collection system. The mold arbor for casting the plaster of Paris molds is machined on a lathe from a 3/4 inch diameter solid black Delrin plastic rod. A 3.5 inch long blank is cut from the rod and faced on both ends. On one end, a center hole is drilled, followed by drilling a 5/16 inch hole, 1.5 inch deep. The hole is tapped with a 3/8 to 16 straight thread for the flathead machine screw that will attach the arbor to the mold base. The blank is turned around and inserted into the 3-jaw chuck, sticking out far enough to permit machining the stem. The stem is machined with a 1/4 inch radius carbide cutter. The length of the stem is 7/8 of an inch on the flat before the 1/4 inch radius begins. The stem is turned with successive passes to achieve the desired diameter. The stem diameter is the only critical dimension because it controls the diameter of the bulb stem, which must slide into a 10 millimeter graphite compression fitting. The shrinkage of the ceramic must be taken into account so that the stem diameter on the mold arbor is sufficiently oversized. The shrinkage is different for different ceramic materials, but the material used in this one demonstration is Edgar plastic kaolin, which has a shrinkage of 6.6%. Therefore, the diameter of the stem on the mold arbor is 0.43 inches, 10.92 centimeters. The arbor is attached to the mold base with a 3/8/16 flathead machine screw. A section of 1.5 inch PVC pipe 4 inches long that has been slit lengthwise serves as the outer sleeve for the mold form. The sleeve is inserted over the step in the mold base, which has a slightly larger diameter than the inside of the sleeve. A piece of painter's tape is applied to the slit to prevent plaster of Paris from leaking out, and a hose clamp is applied to the base and tightened securely, making an enclosure for the liquid plaster of Paris before it sets up. The mold material is a type of plaster of Paris called perfect cast. It entraps fewer bubbles and is much stronger than the traditional plaster of Paris commonly used for making slip casting molds. For the top mold, 150 grams of perfect cast are measured into a plastic mixing bowl. Then 50 grams of water are added, in the ratio 3 parts plaster to 1 part water. The mixture is stirred with a rubber spatula to disperse the powder and eliminate as many lumps as possible. A few small lumps is generally not a problem. If the mixing is too rigorous, however, excessive air bubbles may be introduced. The working time for the plaster is about 2 minutes before it begins to set. The mixture is poured into the mold to just cover the top of the arbor. This would be a good time to mention that plaster should never be poured down the drain. Excess plaster in the mixing bowl should be disposed of in a proper container. The mixing bowl and spatula must then be rinsed in a bucket of water before final rinsing in the sink. plaster sets in about an hour, at which point the hose clamp and painter's tape may be removed. The sleeve is removed by inserting a screwdriver into the slit and twisting to expand the sleeve and permit it to be raised from the casting. The flashing resulting from plaster getting into the slit may be scraped off with a knife or razor blade. In order to extract the arbor from the mold, a handy trick is to place the mold in a freezer for about 30 minutes. This results in a slight expansion of the plaster mold with respect to the arbor, permitting easy extraction. The base end of the mold is flat and perpendicular to the arbor axis. The sharp edge should be filed with a radius break using a flat file to reduce the chance of chipping the plaster. The top end is faced off in the mini lathe until the 10 mm stem hole is exposed. This flat surface will aid in scraping off the slip overfill after slip casting. The sharp edges should be removed with a file as well. The mold for making bulbs is a two-part mold, commonly used in slip casting where there is an undercut. Without a split mold, it would not be possible to extract the bulb. The mold design requires that the barrel of the two mold halves join concentrically. For this, registration indents are machined into the top mold surface where the two halves join. 3 dots are made with a Sharpie marker at a midpoint between the mold ID and OD. The location of the indents along the radius is immaterial since the mold halves form a unique set. The indents are made using a 45-degree carbide router bit chucked up into a drill press. The only concern is that the indents must not be machined so deep that they break through into the mold ID. The mating surface of the top mold with the registration indents is painted with Murphy's furniture oil, diluted with 50% water. All surfaces where the two mold halves join must be coated to prevent the plaster from the bottom mold from fusing with the top mold, making mold separation impossible. The surfaces, including the walls of the indents, must be coated, but care must be taken that no Murphy's oil coats the inside bore of the top mold, or removal of water during slip casting of the bulb will be impeded if the pores of the plaster are plugged. The oil is allowed to dry and a second coat applied if necessary. The mold arbor for the bottom mold is machined in basically the same way as for the top mold arbor, except instead of a 10 mm stem port, the end is machined with a hemispherical dome. The arbor is drilled and tapped with a 3/8/16 thread into which a nylon machine screw is inserted. The major OD is such that when the arbor is inserted into the cavity of the top mold, the arbor makes a tight clearance, slip fit. The nylon screw is used to adjust the length of the bulb as it reaches the end of the top mold cavity. The screw is adjusted for the shortest length in this demonstration. A 3-inch length of 1.5-inch PVC sleeve, split lengthwise, is inserted over the end of the top mold. A marking ring on the inside of the sleeve is used to adjust the position. The bottom mold arbor with the hemispherical end extending outwards is dropped into the mold assembly. Painter's tape is applied along the slit and a hose clamp is attached just below the end of the top mold to ensure leak-proof enclosure. 75 grams of perfect cast plaster is mixed with 25 grams of water and mixed with a spatula until fully blended. The plaster is poured into the mold assembly to the top of the PVC sleeve and allowed to set for about 1 hour. Cleanup of the mixing bowl and spatula is the same as for the top mold. After about 1 hour, the hose clamp and painter's tape are removed. Gentle pressure on the bottom mold half causes it to separate from the top half, with protrusions matching the registration indentations. The end of arbor with the nylon bolt should slide out of the top mold. The arbor must be extracted from the bottom mold carefully. The mold may be placed in the freezer for 30 minutes. Otherwise, aggressive force to remove the arbor may result in fracture to the plaster in the join region. 4 mold sets have been prepared. The mold halves are fully dry and ready for slip casting bulbs. The molds have been numbered and marked with an alignment fiducial that crosses the joint. Also, it is a good idea to date the molds so that matching parts from one batch don't get mixed up with parts made on a different date. A bottle brush and rag are used to remove any loose powder from the mold surfaces. The molds are assembled and painter's tape applied to the joint region along the parting line. Then they are ready to be filled with slip. In this segment, porcelain casting slip for making the bulbs is prepared from commercial kaolin powder and water. For this demonstration, the powder is Edgar Plastic Kaolin, EPK, from a quarry in Florida. 300 grams has been pre-weighed in a sealed container. A fully charged Ninja Smoothie blender with lid removed is taired on the electronic scale. 150 grams of water is added, along with 5 milliliters of Darvan 7 deflocculant. About half of the EPK powder is then spooned in. The lid is screwed on tightly, and the Ninja blender activated with rigorous cycling for one full cycle of about 30 seconds. The lid is removed and scraped with a rubber spatula, as well as the sides of the blender. Then the remaining powder is added, and the sequence repeated, scraping the lid and sides to ensure that all lumps are eliminated. 2 additional blender cycles are generally sufficient to incorporate all the kaolin into a liquid about the consistency of thick cream. The slip is poured into a taired plastic squeeze bottle, using the spatula to remove the remaining slip from the lid and sides of the blender. The net weight should be a little less than 450 grams. 2 large O-rings are placed over the squeeze bottle for traction and the bottle inserted into the holder. The holder, rotating at about 30 RPM at a 45-degree angle, keeps the slip mixed without introducing bubbles, which can otherwise result in casting defects. New slip should be continuously stirred in this manner for about 24 hours before use. With all 4 molds prepared, they can be filled with slip. For evacuating the slip after the required cast time, which determines the bulb wall thickness, an apparatus for draining the mold interior is used. The apparatus includes a collection cup for recovering the drained slip and a 1/8-inch tube connected to an aquarium pump that extends into the interior of the bulb serves as a vent. Without this, a vacuum forms inside the bulb when the slip is drained. To drain the mold, it is inverted, positioned over the vent tube, and lowered into the fixture that centers the mold with respect to the vent tube. The slip is contained in a polyethylene squeeze bottle that has been mixing continuously on a paint stirring device to maintain homogeneity and eliminate bubbles. For this demonstration, the slip will be left in the mold for 8 minutes. A timer is initiated and the molds are filled sequentially in 1-minute intervals. As the water is drawn out of the slip into the mold, the level drops, and slip must be added periodically to top off the casting. As the cast time approaches 8 minutes, a razor blade is used to scrape off the top of the mold. At 8 minutes, the mold is inverted and placed into the draining apparatus. A gurgling sound is evidence that the slip is draining properly. After about 20 seconds, the mold is removed from the vent tube and placed on parallel wood drying rails so that any residual slip can drain out without clogging the stem port. From the bottom, it is seen that the stem port is open. If the port is obstructed with slip, it may be necessary to insert a plastic stick into the opening to clear the port. The collection cup in the draining fixture collects the slip drained from the 4 cast bulbs. The amount of drained slip is related to cast time and is an indication of wall thickness. Weighing the cup of drained slip and dividing by 4 provides a simple means of conducting a rough quality assurance step. The bulbs have been drying in the molds and are now firm enough to be removed. The painter's tape is removed and the bottom mold is carefully lifted. Then, inverting the mold, the cast bulb, which has shrunk from drying, slides out. It may be necessary to insert a dowel into the stem port to free the bulb from the mold. The bulbs are slipped over vertical wooden dowels on a drying rack to promote uniform drying without warpage. It is normal to have some flashing at the parting line. This will be removed once the parts are dry before firing. After drying for about 24 hours, the flashing is removed using a fine-tooth flat file. The bulbs are loaded horizontally in the furnace into 1-inch diameter ceramic shrouds that keep the bulbs from rolling into the furnace elements and provide protection from temperature hotspots within the furnace hot zone. The bulbs are fired with a temperature profile having a slow temperature ramp to the peak temperature of 1000 degrees C, where it is held for 1 hour. The complete cycle takes 14 hours. Once the bulbs have been fired, they are strong enough for rigorous handling. A polyethylene sleeve that has been machined to match the OD of the fired bulbs and slotted lengthwise is positioned over the stem end of the bulb and clamped into the 3-jaw chuck of the mini-lathe. Even though the ceramic is hard and durable, the bisque-fired porcelain is easily sanded to remove surface defects, with 400 grit sandpaper followed by 1500 grit emery paper to the desired surface smoothness. The bulb is turned around in the sleeve and the end with the stem is similarly sanded. The stem port is sanded until the diameter is about 9.8 millimeters and checked to ensure that a 10 millimeter graphite ferrule slips over the stem without interference. As this is the only critical dimension, a good fit is essential for making a gas-tight compression seal. The last step is to trim the open end of the 10 millimeter stem, which has been made about 1/4 inch longer than required to allow for the length to be trimmed to the final length. This step gives the open end of the stem a clean surface and prevents the stem from extending too far into the compression fitting, where it can be easily fractured. The bulb is immersed in water to fill pores prior to trimming. A gauge block is used to set the final length. Using a diamond cutoff saw, the end is trimmed so that it protrudes out from the compression nut about 1 millimeter. For the final step, the bulb is ultrasonically cleaned to remove any clay particles from the pores left over from the sanding operation. Then the bulb is dried in air at 200 degrees Fahrenheit and sealed in plastic vial for final use. The microporous membranes described in the previous segments have many potential applications, but one of the most important is as catalyst supports in microporous membranes reactors, MMRs. This instructional video shows all the steps for infusing catalytic nickel nanoparticles into the bulbs for making these devices. These bulbs have been ultrasonically cleaned, dried, serialized, and stored in plastic vials. This follow-on video demonstrates how to turn the bulbs into microporous membrane reactors suitable for ethanol steam reforming. This segment shows all the steps for infusing nickel catalyst into the bulbs for preparing nickel nanoparticles. First, the dry weight of each bulb is recorded. The bulbs are placed upright in a beaker, and 1.5 molar nickel nitrate solution is sucked into a 50 cc syringe. The needle is inserted into the stem port and solution injected until overflowing. An interesting characteristic of the porous bulbs is that the water solution readily wicks into the pores by osmosis. Once the solution permeates through the wall, the exterior surface darkens noticeably. This takes 1 to 2 minutes until all the pores are filled with solution. When complete, a rubber tube is inserted into the bulb interior, and with the bulb inverted, the nickel nitrate solution is expelled by blowing into the other end of the tube. The bulb exterior is dried superficially with a paper towel, and the immersed weight is recorded. A bulb with 10-gram dry weight having 35% open porosity should take up about 3.5 grams of solution. The difference in infused versus dry weight is an indication of how effectively the infusing solution infiltrated the open pores. In the case of this first infusion, the average percent weight gain for the 3 bulbs shown here was 28%, meaning that 80% of the pores were infused by nickel nitrate solution. For the first calcination, the bulbs are enclosed in an aluminum foil boat and placed in a 2-inch diameter quartz tube in the center of the furnace hot zone. Calcination decomposes the nickel nitrate, liberating nitrogen oxide gases and leaving nickel behind, evenly coating the surfaces of the microQS ceramic structure. The calcination temperature profile is 25 to 500 degrees C in 1 hour in air, 1 hour soak at 500 degrees C, followed by cooling back to 25 degrees C in 1 hour. Each infusion results in about 20 milligrams of nickel per gram of bulb. The target nickel loading is 60 milligrams, so 3 infusions are required. The subsequent infusions are performed in exactly the same manner as with the first infusion. After 3 infusions of these bulbs, the bulbs are noticeably darker than the original bulbs. Nickel weight gain was 63 milligrams per gram of substrate. It has been found that this much catalyst loading is ideal for MMR operation for ethanol steam reforming. The nanoparticles are about 25 nanometers in size, so resolving them requires high magnification with a scanning electron microscope. Zooming in from 8000x to 60,000x confirms the existence of these tiny particles decorating the surfaces of the kaolinite grains. The nickel particles are only about 1/3 the size of a coronavirus. An estimate of the number of such particles per cubic centimeter of substrate is about 100 million.